Periodicity part 4. Maybe we're getting near the end. I don't know if I can do it all, and hopefully in one. I'll try hard. But this is going to mostly focus on ionization energy. I didn't really write that. Well, actually, periodic law radius, IE trends. I put the whole thing, but mainly IE and something called electron affinity I might mention. Okay, so just continuing on. First, let me look at your worksheet for a second. I wanted to show you something on the first page. You should be able to answer these right now, but if I didn't officially assign it because I wanted to kind of review and tell you something about it. You may have seen this early in the year, or I usually go over it in Unit 1, but we didn't talk about it a whole lot here. But I'll just show you this for a second. Okay. So let's just say that you have in a system a positive and negative particles separated, like positive 1, negative 1, we'll say. And here you have positive and negative 1 together. Okay. Where would you say, which one is more stable, lower potential energy? Okay, more stable, lower potential energy. Stable means it's not going to react or move. How about that? It's not going to move. It's not going to change. Not going to change. So would this stay the same or change? Okay. Would this one stay the same or change? All right. Who's more likely to stay the same? This one is more stable. Because remember, positive, negative, opposites will attract. Well, if they're attracted, they can't really be any more attracted. I mean, I guess I could draw them as close together as possible, we'll say. They can't be any more connected than that. So this would be low potential energy, more stable, high stability, you might say. Those are always better words for AP students to use in the essay too. To have a lower overall potential energy for the atom, or to have more stability. Don't say, well, fluorine likes to gain 1 electron, because then it will have a full shell and it will be happy, like the noble gas. That they hate to hear that. They absolutely hate hearing that, okay, on AP. Because it will be more stable. It's a more stable arrangement. When it gains 1 more electron, it's more stable electron-proton arrangement, so it will not react. But without that, fluorine wants that electron, so it wants to react till it gets it. If you remember that. Don't worry if you don't remember the fluorine example. All right, in this one, you'd say here is high potential energy, and it will be less stable or unstable, because in the very next moment, what's going to happen is they're going to fly together. If I wanted to have a positive and negative separated like that, I would have to actually physically have something to hold them in place, or something blocking them in order, to keep them where they are, to suspend them. But as soon as I let my hand off, boom, they're going to go together. So this is temporary. It's unstable. It's high potential energy. Now, in some conditions, that might be more stable. Like you might remember back from we talked about. Well, in the gas law chapter. If I were to have really, really, really high temperature and they start moving around crazy, well, then it's possible that might be the most stable in that high temperature. But anyway, given the same circumstances, that would be more stable than that. Okay, all right, if they're all in the same conditions. Okay, so it just says, like, for example, look at one of these diagrams. Does it represent high or low potential energy? Then it says, if these particles were to join together, would energy be absorbed or released? Okay, so think about this. If these join together, positive to negative, it goes from here to there. Does that require energy, or will energy be released? It has to be one or the other. If it requires energy, it's called endothermic. It requires or absorbs energy. Now, you already know that from AP, but actually, if you're in general chem, you didn't know that perhaps, or honors should have known that too. Exothermic means it releases energy. Energy. Or it could be heat, because that's what the word therm. It's usually in the form of heat. But it can also be in the form of light. So exothermic is just used. Exothermic, it releases. Endothermic, it requires it. So if actually I do have one magnet. Oh yeah, this might work. I can just show this. Yay, this works. Oh good, I finally have one thing I can show you. All right, look at this. This is a magnet on this metal piece. Now, if I want to separate them, is that going to be exothermic or endothermic? Does it require energy, or will it release? Well, it requires. Look, I have to pull them apart. Okay, I pull them apart. So that's endothermic to separate them. That would be like that. If I want to separate these two that are joined, it's always endothermic to break a bond, to separate things. You got to add energy, like to make things break apart. Now, if the things just come together, I guess I can kind of do it there quick enough. Well, how can I put it close enough to my hand and see? Oh, that's not too great, but oh well. But if they join together, energy is released. So energy is released when they join together. So exothermic that's when they came. Exothermic would be when they fall together like that, and endothermic when you separate them. Now here, obviously, I can use gravity and show you. If I let go of that, it fell down. And so what that was exothermic, because gravity, potential energy of gravity, changed and pulled it down. So gravity pulled it. That was exothermic. Sorry. Now when I pick it up again, that will be endothermic. All right. I'm just talking too much, too fast. I know I do that a lot. I'm sorry. So it just has 4 situations. Like you might have positive, negative, positive, negative. I could have positive, positive, or a positive, positive there, or a negative, negative. Now suddenly that's not low potential. Now this is unstable. In the very next moment, it's going to fly apart. So, the very next moment, it will be an exothermic process. So, okay, I just wanted to show you those 2 words to start off this lesson. Now, if you go into, that was 7:14. I didn't number it, but, oh no, that was 7. I'm sorry, that's wrong. 7:15. Oh, I even put that dreaded word happy. Happy and stable. Don't use happy. I wrote that. I already told you about 7:14 in a previous lesson, how atoms want to either gain or lose electrons to have a full valence shell, to become isoelectronic with a noble gas. In doing that, there's a more stable configuration, a more stable distribution of electrons around the protons. So around the electron hotel rooms, they like to have them all full. Okay. So exothermic, endothermic processes. That was 7:15. Oh, and I didn't even talk about this too. I better write this down, because again, this is something for general that they never saw. In an endothermic reaction like this one, 180.5 kJ. This is heat plus nitrogen plus oxygen gives you 2NO. All right, this is kilojoule. Is a metric unit. You can also use calorie if you wanted to. You've heard of calories. That's an English unit. Now, they have to be converted. I'd have to calculate what that is. But if you add this to nitrogen and oxygen, you get NO. That is an endothermic reaction. Now, for an endothermic reaction, we have something called delta H. It's actually called enthalpy. And AP students, this is a review. You already know that. You think, oh, yes, I know. The enthalpy would be positive 180.5 kJ. In fact, we don't even write positive. We just write positive. That's it. Meaning, for this to happen, you have to add energy as a reactant into the system. In fact, in the room right now, you have nitrogen, oxygen all around you, but it's not going to give you this coughing, pollutant kind of gas. Instead, if you add an amazing amount of energy for every mole of this and this, then you get that to occur. So you have to add energy into the room for that to happen. Now, on the other hand, exothermic reaction is, here's an example, carbon, like burning coal. Coal can be considered like charcoal. Coal can be like burning carbon. And when you do that, you get carbon dioxide and water. And you know what? Oh, you don't get water. I'm sorry. I was thinking of a hydrocarbon. This is only carbon. Okay. If it were, okay. This is correct now. I just said it without looking and thinking that better. Okay, so carbon burn will give you carbon dioxide. Now, when that happens, like when you burn charcoal, do you get out heat? It's true you put a little match in there, but compared to that little small match, that little spark you light it, think about what you get back from it. You get back a whole lot more energy. You get back. That's called exothermic reaction. Now, an AP student might remember, when I light the charcoal, what is that called? What is that energy called? It's called the activation energy. It activates it. It's a small little spark of energy, but then you're going to get out a ton of energy, And it says on this one that you get from burning coal 100. Well, I put the same number, 180.5. Maybe I found this somewhere. It will release the same amount. I'm not sure if that's. I have to look it up where I got that from. But anyway, what this means now, exothermic, the delta H value for this reaction is negative 180.5 kilojoule. So if you ever see a negative enthalpy, then remember, you're only going to see either this or this. Like you'll see a reaction with that next to it, or you'll see that one. You're not going to see both. Same way, you'll either see this reaction with that number, or you won't see that number, you'll see that written in it. And that's what you see on the next worksheet. And it just has, so you should be able to do that as well now. Endothermic and exothermic reactions. Well, anyway, just label, is this endo or exothermic? That's all you got to do. That's no math or anything there. And the last one, H, is actually a nuclear reaction, which, well, you can just see how it looks. You get an amazing amount of energy there. Okay, so now for ionization energy. What in the world do we mean by ionization energy? I know all these videos, it's a lot of information, but okay, ionization energy. But the work you do is pretty easy compared to all the other stuff. And isn't it amazing? In this chapter, the hardest thing was electron configuration. Well, you might say the math was harder. I don't know what you think. But this is definitely the easiest, and it's the last section in the chapter. Okay, so IE, ionization energy, is the energy. All right, I'm going to read the official definition first, and I'll tell you kind of off what you can think in your mind. It says, the amount of energy needed to remove the outermost electron, or least tightly held electron. It should say this. No, it should not say single mole. From a mole of atoms in the gaseous state. It's the amount of energy needed to remove the outermost electron from a mole of atom. Don't put single atom. A mole of atom in the gaseous state. That's why when you look below it, IE means ionization energy. And you see it's written in kilojoule per mole, kilojoule per mole. You could calculate it. That is not, that definition is not the official one. Amount of energy to remove the outermost electron from 1 mole of gaseous state, atoms. Okay, here's what we mean by that. So let's start with magnesium metal. You see on the paper, it says IE 1, 2, 3, 4, Mg, and Cl. So let's see a magnesium atom. This will be easy, okay? Just hold on with me. Magnesium has a 12, that means it has a positive 12 nuclear charge and 12 electrons. So magnesium has positive 12 nucleus, 12 protons, and it has 12 electrons outside here. So I'll put negative 12. Think about it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now that's not the way they're arranged. We know that it's 1s2, 2s2, 2p6, 3s2. Is that right? Yeah, that's what it would be. Well, but I just did this for our purposes here. Okay, so here's the deal. When you add energy to the magnesium atom, if you want to pull an electron away, let me say it that way. If I want to pull an electron away from magnesium, let's say I want to change magnesium to Mg plus 1. I want to take it away an electron, so I'm going to have 11 electrons, and I still have 12 nucleus. So I'll put there. So remember, negative 11 and positive 12 gives you positive 1. We did that in an older chapter. If I want to pull an electron away, am I going to have to add energy, or will energy be released? I have to add energy, right. Well, the amount of energy that I need to add is called the first ionization energy, IE1, the first ionization energy. Now for magnesium, and I know there's one wrong number in these notes, unless I fixed it. It says 738 kilojoules per mole. All right, if I want to take away 1 electron from magnesium, so what it means is I'm going to add 738 kilojoules. I say 1 atom, well, from 1 mole. It will be 1 mole. The reason why they use 1 mole is just because they want the numbers to make sense. I mean, otherwise, 738, we can imagine that number, imagine it like money, like $738, they'll take away an electron. Okay, that makes sense. But if I wanted to only know one atom, 738 to take 1 mole of magnesium electrons away from a mole, 6.022 10^23 atoms. You got to take all their first electrons away. You got to add that much. Well, otherwise, I got to divide this number by 6.022, and that number is not really comprehensible in our mind. That wouldn't make sense. It'd be so small. Well, here's a way I like to tell everybody to remember it too. Well, I'll get to that in a minute. I'll tell you now. It's like teeth, okay? And there was a goofy little story that I would always tell about some students, and I would just say that, oh well, I'll have to make up some names. Oh no, I don't know who I'm going to use. Johnny, I'll use for a boy, and for a girl, I'll use, I don't know, Anna and Johnny, whatever. And so let's just say that Johnny, when he was walking around one day, and he going to class, he says, and Anna comes up to him and says, Johnny, I really like your teeth a lot. My teeth? He says, yeah, I like your teeth. He said, I wonder, could I buy one of your teeth from you? And Johnny's like, well, you're crazy. You're psychotic. What is that? Well, I just thought about it. I got to get my wisdom teeth taken out next week. I'll just sell one of those. So, okay, yeah, I'll sell you a tooth. Okay, well, how much? Well, okay, $738. So Johnny says, Anna, you can buy my tooth for $738. So she buys the tooth, and then just say she puts it like on a necklace on a string, and she's like, swinging it around and wearing it and stuff. And everybody sees her. This is a very strange story, I know. I just try to you'll remember this probably. So everybody sees her, and then, I don't know, what's another girl that can be in the class? Or it could be a guy, too. It could be a guy. It could be Brian, okay? Brian comes up and says, Anna, where'd you get that tooth? Oh, I bought it from Johnny, for $738. Really? Me and Johnny are real good friends, man. He had to sell me a tooth, too. So he goes up to Johnny and says, hey, Johnny, can I buy one of your teeth? Brian says, can I buy another tooth from you? And he says, well, I had to have 2 wisdom teeth out, yeah, but I tell you what, I'll charge you 1225.9. This should be IE2 on the paper. There should be a 1 in front of that number. I'll leave it there for a minute. 738 to the first person. To buy tooth number 1, it costs 738. But number 2, that should be a 1 in front of that. Okay? Let me see if I have a pen. I can fix mine too. That's not a good model to hold it up. Oh, here it is. Because it's a misprint. And it's impossible too. I should have done it with red. But oh well. There it is. So it should be 1225.9. And then 7,733 for the third tooth. And for the fourth tooth, 10,546. So wow. 700 to 12. And then you go to 7,733 for IE3. And it continues on. Actually, there will be, since magnesium has 12 electrons, there will be 12 prices or 12 ionizations. IE1, IE2, IE3, IE4, all the way to IE12. If you had an atom like gold, and I want to take away all the 79 electrons of gold, there'll be IE1, IE2, all the way up to IE79. All right, and each one gets higher and higher and higher. So think about that. Why does it get to be more and more and more as you increase? Well, one reason why is, you remember the little girls in the circle. Every time you take away an electron, the atom gets smaller. That is true. You take away an electron, the ionic radius gets smaller and smaller and smaller and smaller. And now there's less shielding between the nucleus and the outer electron, and so therefore it's going to be easier to remove. See, this is a strange trend. I'll have to go back to this in a minute. I didn't tell you the trend yet, but I'm just talking about what it is, first of all. So first pattern you should know. For every element, that's true. Now, for every element, like for chlorine, it says electron number 1 will come away with 1255 kilojoules per mole. Then what you have to do is have chlorine. It has to be chlorine, gaseous chlorine, not Cl2. It has to be the Cl gaseous. And then you'd have to have to 1 mole of it and add 1255 to get away the first electron, 2296 for the second electron, and then it was 3850 for the next electron. Okay, so it goes on and on. That's also interesting that that one is higher than that one, but we'll talk about that in a little bit too. So every element, each ionization energy takes more and more because the atom's getting smaller, and in the same way we talked about earlier, it takes more energy to pull the electron away. I probably should have told you, and maybe I'll say it now, what's the trend for ionization energy? Okay, so on the chart, we talked about this already. It's a lot like radius. Remember, the radius decreases as you go from left to right. Well, ionization energy, the first ionization energy, they only talk about the first one, because that's the one we really compare the trend to. It will increase. So, if you have a small atom, it's harder to take away the electron. All right. So if I have an atom here, let's just say I have an atom and there's an electron, like, I don't know, 100 yards away. That wouldn't really be true. 100, whatever you want it to be, units. 100. I'll use nanometers. How about that? Okay, if I want to be just real nerdy about it. Nucleus, 1 electron, like a hydrogen atom. Well, here's another one. Here's a nucleus, and now let's say the electron here is only 10 nanometers away. Well, since it's closer, according to Coulomb's law, and here's where Coulomb's law does come into play. If you have a small radius, then your energy of attraction is going to be greater. So it takes a lot more energy. This is held real strong compared to that one. So I've got to put a lot more energy to pull it away from a small atom than a large, simply because it's closer in proximity to the nucleus. All right, that's one reason. And the other, all right, that's really the main reason on the chart. Well, that's the reason why this gets larger, higher and higher. As the atom gets smaller, each ionization gets higher. But on the periodic table, remember, as you go from left to right, like if I compare magnesium on the periodic table, and way over here in the same period number 2, it was period 3, sorry. Here's magnesium, period 3. Here's chlorine in period 3. Which one would have a higher first ionization energy? It's chlorine has a higher, because it's a smaller atom. Since chlorine is smaller, it's harder to take away its outside electron than magnesium. Now, I know they have different nuclear charges, but because their electrons are at the same level, so it's the same. It's actually the same reasoning you want to use that you use on the size. Magnesium and chlorine. Which one has a higher first ionization? Well, first you'd say magnesium has a nuclear charge of positive 12. All right, positive 12 nucleus. Chlorine is a positive 17 nucleus. The outermost electron for magnesium is at the n equals 2 level. It's 3s2. N equals 3. Sorry, n equals 3 is 3s2. So if you want to say it's, neon 1s2, 2s2, 2p. Oh, no, it wouldn't be that. What am I doing? It'd be neon. That's a shortcut, 3s2. But chlorine, on the other hand, if I jump over here, is neon 3s2, 3p5. And it's also n equals 3. Now, it's not such a big deal that one has only 2 and one has 7 electrons. The bigger deal is that they're both at level 3 and that one has a positive 17 nuclear charge. So, in other words, chlorine is a much smaller atom. Let me just write it here. Much greater nucleus. Its electron, it's a smaller atom. It's closer to the nucleus. So, since it's closer to the nucleus, just like gravity, the closer you get to the Earth, if you're farther away, the closer you get to the higher weight, farther away is a lower weight. Because the electron is closer to the nucleus, it has a it has a greater first ionization energy, greater energy of attraction to overcome. If I want to break it, I got to put in more energy to take it away. Okay, now going left to right, that's the general trend. As you go from left to right, because they're both at the same level. Now, there's something I'm going to throw in a minute, some exceptions. Now, on the other hand, when you go down a group, like say from magnesium, what's below magnesium? And by the way, let's remember now, when you're going down the group, level 3. So really 1, 2, 3. If I wanted to, I could do the same thing there. They both have at level 3. As you go down, though, let's say under magnesium is calcium. We have 1, 2, 3, 4. And the outer electron of calcium, which is positive 20 nuclear charge, is at N equals 4, because it will be argon 4s2. So, now, if I'm comparing magnesium and calcium, which one has a higher first ionization energy? Number one, you'd say, well, magnesium has its electron located at N equals 3. The outermost electron is 3s. All right, Ne3s2, positive 12 nuclear charge. Calcium does have a greater nuclear charge of positive 20. However, its electron is shielded from the nucleus. And that's important to bring up. Shielding is a very important thing. Because remember I told you, shielding can also be considered, all of this is negative, a negative electron cloud. This is inside. Outside it is another layer electron cloud. Okay, a shell. We call it shell sometimes. All right. One, and then inside is another one. So this electron is shielded from the nucleus by this electron in the N equals 4 is shielded from the nuclear charge by the N equals 1, N equals 2, and N equals 3 shells. But the magnesium electron at N equals 3 has less shielding, only shielded by the N equals 1, N equals 2. So having less shielding makes the atom smaller. Or another way, having more shielding makes the attraction, the nuclear attraction to that electron, very weak. So even though there's a greater nuclear charge, it's being blocked. So because it's outside at N equals 4, it has a lower first ionization energy. And I'm telling you all these things. How am I going to write this down? The main things you should write down in the essay are, what's the nuclear charge, where's the outermost electron, and what's the electron configuration, the short form, and then consider the amount of shielding. All right, and shielding really only matters, well, I'm going to talk about an exception in a little bit, but it really only matters going down the chart. If you ever say, magnesium is calcium's a larger atom because it has more shielding than magnesium. Well, that's true, but I want you to, whenever you say the word shielding, I want you to tell me who is shielded by what. Calcium has more shielding than magnesium because calcium's outer electron is at N equals 4, and it's shielded by the N equals 1, N equals 2, N equals 3 layers. I want you to tell me those are shielding the N equals 4 electron from the nucleus, the greater nuclear charge. Magnesium, on the other hand, with a 12 nuclear charge, its outer electron is only shielded by the N equals 1, N equals 2. So less shielding there. So the main things to talk about are the amount of shielding in the group. More shielding means it's going to be a larger atom because you're holding more weakly the electron. It's a weak hold. Shielding is one reason, and the other reason, and you can also bring it, is because it's farther away from the nucleus at N equals 4. So that does matter as well. Being farther away, this one is only at N equals 3. So one's at N equals 3, one's at N equals 4. Oh, being farther away is going to make it larger. One has shielding from N equals 1 equals 2. The other has shielding from N equals 1, 2, 3. Oh, that also makes it a larger atom. So there's double, two things you can bring up about that. And, okay, now going this way, we just talk about mainly they're at the same, pretty much the same level, N equals 3. But that one has a greater nuclear charge, positive 17. The greater nuclear charge makes the atom smaller, and therefore a smaller atom is going to have a greater ionization energy. Going to need more energy to pull the electron away. Whew, that's a lot of stuff. All right. I pretty much told you the entire trend. And here's the only exception, and I've almost got it there. There's only one exception to bring up, and I'll just tell you the one. You know what? I'm going to tell you the one exception that I'm going to have to make one more part to this video. And I'll talk about electron affinity, and I'm going to finish part of ionization. But let me tell you one more trend. On the periodic table, this is true. Ionization energy increases to the right and up, as I showed you. However, when you go to the right, there's two columns you need to be aware of. For any period, group number, it tells you on the paper, within any period, Group 13, IE1, is less than group 2, IE1. All right, let me give you an example of that. So group 13 is always less than group 2, IE1. So let me use an example of boron and beryllium right here, boron and beryllium. So you would expect lithium is a low ionization and the neon is the highest. So it gets higher, 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 higher. Smaller atom, higher ionization. But one trend is this is actually lower, it's an exception to the rule, than beryllium. Boron is lower than beryllium. Boron has this outer electron configuration. Helium, 2s, it's helium, what is it? 1s, 2s2, 2p1. All right, so it's 2s2, 2p1. Boron looks like that, but now beryllium looks like this. Helium, and then it goes 2s2, and it has no electrons there. I like to draw this to show you. Okay, so why is boron easier than beryllium? And the reason, notice this. Beryllium has a full 2s shell, nothing in the 2p, but this has one electron in the 2p. Well, I mentioned a little bit of it before about the penetration effect earlier, but I'll just say this. There is shielding between 2s and 2p. So 2p is a little bit higher energy than the 2s. Sometimes they draw it like this one here, and there's like a little bit higher staircases to show the 2p's. Well, anyway, this is blocked. It is shielded by the full 2s. So because the 2p1 electron of boron is shielded by the 2s2 full electrons, it is easier to remove it because it's like repelling that. It's easier to remove it, so it has a lower first ionization than beryllium. So if you're asked for anything for 13 to 2, it could be beryllium, boron, magnesium, aluminum, calcium, gallium, all the way down. You ought to draw this, what I showed you. And then hopefully that'll ring a bell. Oh yeah, I remember that electron is going to be blocked, going to be repelled and shielded. Shielded is the magic word by the 2s2 electrons. The 2p1 electron is shielded. You can say the 2px1 electron if you want to really be whatever technical detail about it. All right. The other exception is it for any period. And any period, it tells you on the paper, group 16 is less than group 15. All right, group 16. Now, this is 18, 17. 16 is less than 15. 16, which has oxygen, is less than 15, which has nitrogen. So let me do oxygen and nitrogen. I'll just do those two for you. 16, where it has oxygen, is less than nitrogen. So oxygen and nitrogen. So let's do the same thing for oxygen. The electron configuration of oxygen, I'm going to go and do this. It's helium. Then I'm kind of doing an electron configuration in an orbital configuration. It's 2p4. 1, 2, 3, 4. So 2s2, 2p4. But for nitrogen, it's helium, 2s2, 2p3. Can you see something interesting? So we're saying it's easier to take an electron away from oxygen. To take the first electron from oxygen is easier than it is to take it away from nitrogen. And the reason why is because of this right here. Because the 2px is a doubly occupied orbital. The oxygen atom has one doubly occupied orbital, but these are all single occupied, the p's. So what happens is, remember, their spins are not perfect. They're not always perfect. And so there is some amount of repulsion between them. So that little bit of repulsion just adds enough to make it easier to pull an electron away from oxygen than nitrogen. And you need to always, if you're ever explaining it, you need to show the configurations and as I did there. All right. So you should be able to now do on the worksheet, well, finish all the front worksheet. And then on this one, I told you to do everything, but don't do number 4 yet. I'm going to come back and tell you number 4 with electron affinity. It'll be a short thing. It'll be a short video section. All right, I'll see you.